Hello and welcome back to Ganesh Institute. In today's video, we are taking up another topic from linear algebra, which is vector spaces. Let's say you have a non-empty set. That means it is not empty, it has certain elements. Let's say v1, v2 and so on. So this non-empty set V will be considered as a vector space if it satisfies two conditions. First of all, these elements, when interconnected with each other through operations like addition or multiplication, then this non-empty set will be regarded as a vector space if the result of addition and multiplication will also be an element which belongs to this set. So let's take up an example and see how we can prove it. Let's say if there are two elements of set V, this is capital V, and it has V1 and V2 as two of its elements, and we want to show or prove that whether it is a vector space or not. So what you have to do, you have to add this up, add V1 and V2, and let's say you get some result, let's say W, and if that W also exists in this set, then you can say yes, it follows a closure property. What is closure property? That the result of any operation also belongs to the main set. Because this W also belongs to V, the main set, that's why this V can be defined as a vector space under operation addition. Okay? And let's say if we talk about the multiplication, if we do the multiplication of V1, V2, and we got another element, let's say Z, and if Z is also present in this set, then this scalar multiplication will also be closure, because the result belong to the main set. Therefore, this is also a vector space. Okay, so to be a vector space for any set, the elements must follow firstly the closure property. That means if you are adding or multiplying with any scalar, then the result should also belong to the main set. And the second property to be a vector space is that operation which you are doing, to have this V as a vector space, the space should follow these qualities. Firstly, commutativity. That means if you add the elements of a space, of a vector space, then the addition should be commutative. A plus B should be equal to B plus A. Then it should be associative under the operation of addition. That means if you have three elements in the vector space, then doesn't matter whether you change the order. You can add last two and then to first, or first two and then add it to third. But the result will be same. This property is associativity, so that should also be followed. Then there must be a zero vector existing. So let's say V1 is an element, and if we add a certain number or element which can give us the same element, then that will be a zero. Okay, zero vector. So there must be a zero vector for that particular vector space. Then distributivity should be there. Distributivity means, let's say if we talk about the operation addition, you have addition of two elements and then a scalar multiplication. So you can distribute it like this, right? There must be an additive inverse, that means a negative vector. This is the fifth rule which a vector space follows. So negative vector means if you have an element, you should have another number which will be the negative of this, which will give you 0. Okay? And then you should have, let's say, just now we discussed about the distributivity of addition, right? And it should be distributive in any of the order. If you do the v1 plus v2 and then you multiply with it with r, this is r, okay? v1, v2 plus r, then also the result will be like this, correct? There must be an identity element. What is an identity element? An element, for example 1 in this case, when you multiplied it with the vector element, you get the vector element itself. So this is identity element. This vector space must follow all these properties. It can be anything, just like we have taken v1, v2 as examples. It can be anything, a set of real numbers, a set of complex numbers, anything, or a matrix, or a function, solution of a differential equation, anything. But when it comes to prove it as a vector space, you have to prove all these properties. Okay, so let's see an example how you can solve it. So here in this question, you have to prove that the set of all the real numbers, all 2 by 2 matrices associated with the matrix addition and multiplication is a vector space. So that means you have to prove that all 2 by 2 matrices are a vector space. Okay, if these matrices represent a vector space, that means you have to prove all those properties like commutativity, associativity, identity element. So let's see. We are hypothetically assuming that our matrix is A, B, C, D. Okay. So this is our matrix, a 2 by 2 matrix, and we have to prove that it is a vector space. So firstly, we are checking whether the closure property is there or not for addition and multiplication. So firstly, we are checking with addition of matrices. Okay. So we have this matrix. If we are taking up another matrix, let's say A dash, B dash, C dash and D dash, another 2 by 2 matrix because it is for all, right? And we are adding them. So we are getting A plus A dash, B plus B dash, C plus C dash, D plus D dash. Correct? Now, this is also a 2 by 2 matrix, right? Which means it belongs to V. Because V, that means a set of all 2 by 2 matrix. We have to prove that that set is a vector space, correct? And because it is, the resultant is also 2 by 2 matrix, that means it belongs to the main set V, right? So it is closure for addition. Now if we talk about the multiplication part, whether it is it is showing closure property for scalar as well. So let's see. We are taking up one scalar, right? Any scalar, let's say m, and we are trying to multiply it with a 2 by 2 matrix. Let's see whether we are getting a 2 by 2 matrix or not. So it will be MA, MB, MC and MD. Again, this is also a 2 by 2 matrix which belong to B. So yes, it is showing closure property for scalar. So first condition is satisfied. Next is to show all those properties like commutativity. So in commutativity, what we prove? Let's say we have one matrix A, B, C, D. and another one EFGH. If we add them, okay, and the resultant will be A plus E, B plus F, C plus G, D plus H. But we can write it like E plus A, F plus B as well, right? And similarly C plus G, because in addition order doesn't matter. It's D, H plus D, right? So if you split it back again, it will be E, F, G, H plus A, C, A, B, C, D. So you can see A, B, C, D here in the first part, and in the resultant it is in second counterpart, correct? So that means it is showing commutativity, which says that A plus B should be equal to B plus C. It is following that, correct? Now if we talk about associativity, so in associativity, again take another example, A, B, C, D, a 2 by 2 matrix. Then we are adding it with E, F, G, H. And we have another thing, because in associativity we have three elements. So we are taking another 2 by 2 matrix, E, F, G, H, I, J, K, L. Right? Now if you add this up and change the order, I mean you can write it A plus E plus I, B plus F plus J, C plus D plus H, sorry, C plus G plus K, and D plus H plus L. Correct? And you can see, I mean, you can add first two initially and then add the sum to the right. That means A plus E, B plus F, C plus G, D plus H. And then add it to I, J, K, L. This will also give you this result. Or if you have gone by this, that you want to add last two first, I'm showing you these two first. So it will be E plus I, F plus J, G plus K, H plus L. One matrix, and then add it to A, B, C, D. It will again give you the same answer. So that means it is showing associativity, correct? Then if you talk about the associativity of multiplication, this was addition. If you talk about multiplication, so in the case of multiplication, you have a scalar, let's say M, another scalar N, you have a matrix 2 by 2 matrix, and you want to check for three things whether the answer will be same or not. So initially, if you do, it is Mn, right? Mn, and how you are getting it, if you just simply multiply n with this, Na, Nb, Nc, Nd, right? You can now have M as well, Mna, Mnb, Mnc, Mnd. Again it is a 2 by 2 matrix. You can take out Mn as common, A, B, C, D. So you can see that the order doesn't matter, answer will remain same. So it is showing associativity for multiplication as well. If you talk about the zero vector, another property is zero vector. So for zero vector, you have a 2 by 2 matrix. You are adding it with zero matrix, and you are simply getting the main matrix only, which is a 2 by 2 matrix. So that means it is this vector is this V vector is a zero vector as well. Then if we talk about the additive inverse, that is negative vector. So that means if you take up elements and their additive inverse and add them up, you will get a zero matrix. So yes, this is property, this is following this property also. Then if we talk about the distributivity, there are two sense of proving it. Distributivity of addition, right? And then you can have multiplication as well. So let's say if you have, in both of the cases, you can assume a general 2 by 2 matrix. Because it is distributivity, you should have another element also, let's say EFGH, and you are having a scalar m. So you will see that you can have m a plus e, m b plus f, right? You add this up and multiply with the scalar c plus g with m, and then d plus h, right? And then if you want, you can simply write it as you are having m a b c d plus m e f g h. So you are seeing that it gets distributed, right? It between both of the between both of the matrices of 2 by 2 order. Then you can have distributivity for sum of real numbers. So in this, what you have to do, simply have two scalars, sum of real numbers, any two real numbers, and you are having one matrix, and then you need to simply distribute it, like m plus n with a, m plus n with b, m plus n with c, m plus n with d, right? And then what you can do, you can distribute it like am plus an, bm plus bn, mc plus nc, md plus nd, right? This is one way of doing it. And then you can bring out, you can split this into two different metrics. Like you can have only a with one, like only m with one, a b c d, and n with one, a b c d, right? So this is the distributivity of sum of real numbers. And if you talk about the multiplication, just like we do in identity matrix, identity element, sorry. So in that case, you have to find out one scalar. When you do the multiplication, you should get the same matrix. Because all of the properties are fulfilled, so we can say that this matrix is this set is a vector space. So you can be given with any of the type. You can be given with a function, a matrix, just like we did it in this part. So you just simply have to observe the properties and follow it accordingly. I'm hoping that this topic is clear to you, and if so, then don't forget to like, share and subscribe our channel. Till my next video, take care of yourself. Bye bye.